Okay guys, in this chapter we're going to discuss rotation, and in this video we're going to start off by just learning some background material, which for most of you is a review of what we did last year. So if we've got something rotating, something moving in a circle in rotation, we'd like to be able to describe the motion mathematically, and so we're going to sort of begin where we began when we were thinking about linear systems. So we began initially with displacement, linear displacement. Well, now we're going to begin with angular displacement, or actually angular position is where we'll begin. So this is angular position, which is abbreviated with the Greek letter theta. And we're going to use radian measure to establish angular position, which is defined, hopefully you remember, as the arc length s divided by the radius r. And this is, again, this is radian measure. I'm sort of assuming that you guys are comfortable with radians. If not, we can go over this in greater detail in class, but just do a real quick review. So if we had a 360 degree or full turn, that would correspond, of course, to what we call revolution, or one complete turn. In terms of radians, well, what would the arc length be for a full turn? Well, in a full turn, you're imagining the circumference of the circle, which is 2 pi r then, is your arc length. And we're dividing that by radius, so that yields 2 pi radians. RAD for radians. So 360 degrees, or one revolution, corresponds to 2 pi radians. So half a revolution would be pi radians. If we had 2 revolutions, that would be 4 pi radians, etc. And by extension, 1 radian is equal to about 57.3 degrees, or about 0.159 revolutions. Just sort of a basic relationship between radians and degrees or revolutions. So we probably won't use degrees a whole lot, but we may use revolutions, and knowing this relationship between revolutions and radians will be helpful. So angular position, we can measure the position of something using radians, and that will pay dividends later on. We'll see why that's advantageous rather than using, for instance, degrees. So then after we discuss position, it might be interesting to think about displacement. So angular displacement. Displacement is just the change in the angular position. So this is pretty straightforward, but just so we're clear on the notation, we're going to say delta theta equals theta 2 minus theta 1. So if you have some displacement in position, you want to know the initial position in radian, and subtract that away from the final position in radians. A quick word on sign convention here. Turns out, and this might be a little bit counterintuitive, but the positive direction, we're going to define the positive direction as the counterclockwise direction, and the negative direction as clockwise direction. So if you have something, if you have an angular displacement in the counterclockwise direction, we call that a positive displacement, and if it's in the clockwise direction, we'll consider that a negative displacement. Maybe the opposite of the way you'd think it would be, but that's going to be our notation. That's the convention that we'll be following, and basically that's a convention everybody else follows too. So now we have displacement, we could think about the rate of displacement. In other words, if you have something that's turning, for instance, in rotation, you might like to know how fast it's turning, and this is angular velocity, sometimes called angular speed. The angular velocity is given another Greek letter, which is omega. This is lowercase omega, which is written like a W. Uppercase omega, you might be more familiar with, is this symbol. Lowercase omega is like a W. So this is omega, and it's angular displacement. And we'll define this as d theta dt. we could write that this is instantaneous angular velocity. If we wanted to find the average angular velocity, of course, we could just say delta theta over delta t. Okay, so the angular displacement over time. This would give us the average angular speed or angular velocity. So this is an equation that's going to be important to us. Quick note on units. We'd like to measure this in radians per second. There are, of course, other units that are more common than radians per second. So you might be familiar with RPMs, for instance. RPM stands for revolutions per minute. That is also an angular velocity. It's not the standard units that we're going to use. We're going to stick with radians and seconds, but you might see something like revolutions per minute as a pretty common unit for angular speed. So to continue on, now that we've got displacement and velocity, the next thing we'd like to discuss is angular acceleration. By the way, the same sign convention that we applied to displacement works for velocity and acceleration as well. Again, positive is counterclockwise, negative is clockwise. So that applies for all of these angular quantities. So angular acceleration now, we're going to use another Greek letter. This is the pattern that you're seeing in general. Greek letters are reserved, or no, I shouldn't say reserved, but we will use Greek letters for angular quantities, and our usual Latin letters will be used for linear quantities. So this is alpha, Greek letter alpha, which is used to denote angular acceleration, and so that's d omega dt. Again, not a surprise. Linear acceleration is velocity over time, so angular acceleration is angular velocity over time. And again, we could say the average angular acceleration would just be delta omega over delta t. And in units, again, of course, we'd like to be in radians per second squared would be our units, radians and seconds, to stay with that convention. So this is just a quick introduction to these different quantities. We've got angular position, angular displacement, angular velocity, angular acceleration. And you might, again, see the pattern that I basically just rehashed everything that we did at the very, very beginning of the year for linear quantities, but just now for angular quantities. And we can extend that application. We could keep going with this. And once, back at the very beginning of the year, once we had a firm handle on acceleration, velocity, and displacement, we then did kinematics, and we could extend that too and say derive some equations for angular kinematics. And in particular, I'd like to come up with some kinematic equations that will work for constant or uniform angular acceleration. Uniform alpha. So these are equations that will work for uniform angular acceleration. And let's take a look. I'm going to go through this by, first of all, remembering our really important kinematic equations, our linear kinematic equations. I'll start there. So if we recall the linear kinematic equations, we had four really important linear kinematic equations. So we had, first of all, we said that V equals V naught plus AT. And then we said that position x is equal to x naught plus V naught t plus 1/2 AT squared. These should all hopefully look familiar to you from the beginning of the year. Then we said that the velocity squared would be equal to the initial velocity squared plus 2 times the acceleration times delta x. And then finally the last equation that we had was the displacement x minus the initial x equals 1/2 initial velocity plus final velocity times t. So these are our linear kinematic equations, and we can basically create rotational analogs or angular analogs for these linear equations. So these are going to be our angular analogs for these four equations. So what do I mean by that? I mean that wherever I have an x, I'm going to put in a theta. And wherever I have, doesn't look like theta, does it? And wherever I have a v, I'm going to put in an omega. And wherever I have an a, I'm going to put in an alpha. So rather than linear position, we have angular position. Rather than linear velocity, we have angular velocity. Rather than linear acceleration, we have angular acceleration. And so now I can adapt each of these four equations using those substitutions essentially, and I can say that omega equals omega naught plus alpha t. And I can say that theta equals theta naught plus omega naught t plus 1/2 alpha t squared. Keep going, we can say omega squared equals omega naught squared plus 2 times alpha times delta theta, and then we can say that theta minus theta naught equals 1/2 omega naught plus omega t. And so now I have four very useful equations that are rotational kinematic equations that will remind us that this is only for uniform alpha. So this works only for if you have a constant value for alpha. If you have a varying alpha, these equations don't work, but they do work for cases where you have constant angular acceleration. So they can be quite useful at times. All right, well, we've got a lot of equations here, but we're not done. There is a relationship. The whole point of radian measure, of using radian measure when we're talking about rotation, is to make some sort of a connection between linear quantities and rotational quantities. So let's imagine I've got some rotating disk here. Let's see if I can draw a circle here. Probably going to struggle doing this. I guess that's the best I'm going to be able to do. So here's this rotating disk, and let's imagine that it's rotating in the positive or counterclockwise direction. And now let's imagine we could think about two different points on this rotating disk, right? So we can call this point A, and maybe we'll call this point B. And we could think about these 2 points, and it should be, if this is a rigid disk, so you can imagine like a merry-go-round on a playground. And since this disk is rigid, everywhere on the disk has the same omega. So A and B have the same omega. So I could write omega A is equal to omega B. But clearly, well, maybe it's not. Maybe it's clear. But I think we can see with a little bit of work that the velocity, the linear speed of A, is going to be significantly less than the linear speed of B. And the reason being is that A is significantly closer to the center than B is. In other words, the radius here, this is a little r, and this is a much bigger r. And since this point B is farther away from the axis of rotation, the B is covering this much bigger circle in the same amount of time, right? B is covering this really, really big circle, whereas A is only covering this little circle in a certain amount of time. And since we've been careful about measuring our angular displacement in terms of radians, there's a natural relationship between this radius and the linear length of the circle that A and B are traveling. So what I can say, and maybe this is clear, maybe it's not, I can make the case that the linear velocity v is equal to the angular velocity omega times r. And this works again because I've defined my rotational speed, my angular speed, in terms of radians, which incorporates this natural relationship between linear distance or arc length and the radius. And similarly, I could go ahead and say that alpha or angular linear acceleration a is equal to alpha, the angular acceleration, also times r. So these are two really fundamental and important relationships. Okay, so this is relating linear and rotational quantities. So linear, this v and this a, right? These are linear quantities. That's why we're using Latin letters, and it's pretty simple, pretty easy to translate one to the other. Sometimes we call this kind of speed here, this is sometimes called, this v is sometimes called tangential speed, right? This is tangential speed. And this acceleration is also sometimes called tangential acceleration. And I think the reason is clear. If you look at the velocity vector v, it's tangent to the circular path that the object is traveling in. And similarly, the acceleration vector is tangential. Now, it's worth remembering that we do know of another kind of linear acceleration called centripetal acceleration. So it might be worth thinking about centripetal acceleration, which is not tangential, right? The centripetal acceleration is directed radially inward. So centripetal acceleration, a sub c, we might remember was v squared over r. Well, if you notice, I could plug in for v omega squared times r, right? I could plug that in for v, and I get omega squared times r squared over r, and r cancels out, and I get that this could also be considered omega squared r. That's another way of writing centripetal acceleration. So this thing right here is another way of expressing centripetal acceleration. All right. Well, I think that's enough equations for one day. That's certainly a lot. Tremendous number of equations here. I'm hopeful that for most of you, this is review. This really is the groundwork for a much more interesting conversation that we can have about rotational motion, but it is necessary groundwork. So we'll practice this this week in class.